Oh, okay, today's lecture is on exponential and logarithmic models. And so basically what we're doing is we're really just applying all that we've learned about exponential and logarithmic functions and applying them to real life scenarios. That's what it means by modeling, right? So I'll go over a quick example, or I'll just read a quick example and we'll do it later. But for example, let's say the number of rabbits on a farm is increasing according to the law of exponential growth. The initial population is 8 rabbits, and the number of rabbits doubles every 5 hours. That's very quick. You know, what are they eating, you know? Write a function r of t that describes the number of rabbits at time t, where t is measured in hours, okay? And so exponential modeling, we're going to want to know how we want to write a function to describe these kinds of situations, okay? So in general, an exponential model can be written in this kind of form, right? Let's say we have a function, capital F of little t. In these scenarios, we're going to let little t denote time, okay? Because that's the most common independent variable, right? You guys remember dependent variables from science class? Yeah. Okay, so we'll say f of t is equal to, I'm going to use a capital I here, and that's going to denote my initial quantity. Initial quantity times a, my exponential factor, to the power of little t, time, divided by big T. Big T, which is our period of growth. All right. Yeah. Okay, let me explain what I mean by these things. Okay, this is exponential growth, okay? And we're going to look at decay in a second. This is exponential growth. All right. So, initial quantity, that means the number of things that we start out with at time equals 0, okay? So it could be rabbits, it could be bacteria, it could be money, it could be, I don't know, just ran out of ideas. What are some other things that grow exponentially?
Bacteria.
I just said that. Yeah. Rabbits, horses, antelopes, humans, I don't know. Anyways, that's initial quantity. Our quantity at time equals 0, okay? And we can see that very easily, right? What is f of 0 when t equals 0? That's just going to be I times a to the 0 divided by t, right? And what is this quantity? That's just 1, right? A to the power of 0. And so this is just going to be I. So indeed, I is the initial quantity of our function when time is equal to 0. And then a is our exponential factor, okay? So that would be the amount that the population or quantity is increasing by, okay? So in my previous example, right, the number of rabbits is doubling. So that means my exponential factor is what? 2, right? If it was tripling, it would be 3, and so on. Okay, little t is my time. It's my independent variable. It's the input of my function. And then finally, big T is my period of growth. Okay, so for example, in the previous one, the rabbits, they were doubling every 5 hours. Okay, so that means big T would be 5 hours. That makes sense? So for example, we could look at this. If the quantity at time equal to 0 is big I, our initial quantity, then what would be our quantity at time equals big T? Any ideas?
Would it be 1 though if it's 0, because then it'll be I to the power of Oh, never mind, sorry, I get it.
Okay. F of big T is equal to I times A to the power of big T over big T. Now what is big T over big T? 1. So this is just I times A, right? So indeed, our function is increasing by a factor of A every time that a period of big T elapses, okay? If we were to do f of 2t, what would this be? IA squared, right? You can calculate that for yourself. F of 3t would be IA cubed, and so on. So that's kind of what's going on, and that's what we want to write for these exponential models. So let's do a quick example. Are we all good with the slide?
No. Picture.
Fine. Yes. Yes. Hurry. Okay, let's go back to our rabbit problem. Okay, I'm going to write my function, exponential growth function. Capital F of t equals I a to the little t over big T, right? What is I? Our initial quantity. A, exponential factor. Little t, time. And big T is our period of growth. Okay, in this problem, what is our initial quantity? Big I. 8. We start out with 8 rabbits, right? That's the number of rabbits at time equals 0. What is our exponential factor? 2. Because we're doubling, right? We're doubling every 5 hours. And then our little t is our variable. And then what is our period of growth? 5 hours, right? That's what's going on here. And so this would be our function. Oh, it's little r of t, right? Not f. So this would be our function. And this would be our answer. So we could plug in different values of t and see how many rabbits there will be at various times, right? What is r of 0? 8, very good. What is r of 5? 16, right? We can plug it in. 8 times 2 to the 5 over 5 is 16. What is r of, let's do a fun one, 25? Very good. 2 to the 8 power, right? And so on. So all we need to do to find the number of rabbits at time t is to plug in the number of hours we want. All right. Any questions here? Pretty easy. But let's go on to decay now, okay? Exponential decay. So exponential growth is where we're increasing by a certain factor for every certain period of time. But exponential decay is where we're decreasing by that factor, right? So maybe I could start out by graphing this exponential growth function to see what the decay function would look like, right? So if we were to graph f as a function of t, it would look something like this, right? Our exponential function. Now, what kind of transformation would give us our decay function?
Reflection.
Around?
X-axis.
No.
Y-axis.
Y-axis, right? It would be a horizontal reflection across the y-axis. That would give us our decay. It begins with something big and then exponentially decays to something really close to 0. And so we can really pretty much guess what our decay function would look like, right? Exponential decay. If we were to use the same variables, big F of t, we also have an initial quantity and also an exponential factor. What would be different about the exponent here? Yeah, we would have a negative t, right? Because that's what introduces our horizontal reflection. And it's important to note that this is only decay when a is greater than 1. And I'll explain more about that later. But first, let's see that this is indeed the case, that this is actually a decay function. What is f of 0? F when time is equal to 0. Nope. I, right? Because that's I times a to the 0, which is I, our initial quantity. Okay, so I is our initial quantity. How about what is the value of our function f when time big T elapses? That would be I times a to the negative t over t, which is I over a, right? I times a to the negative 1. And so indeed, after time big T elapses, our quantity is decreasing by a factor of a. Make sense? So this really is decay. F of 2t would be what? I over a squared. F of 3t would be I over a cubed. And so this is decay, right? It's getting smaller if a is greater than 1. Okay? So we can do a quick example. Okay, remember, it's a good convention to always keep our exponential factor greater than 1. Okay, because if a is less than 1, then it wouldn't actually have this sign in order to be decay. And I'll explain more about that later. Let's look at another example, carbon dating. Okay, the amount of a radioactive isotope, carbon-14, decays according to the law of exponential decay. You guys all learned about this in science class, right? A scientist starts with a 10-gram sample, and the amount of the isotope halves every 5,730 years. Write a function, big C of t, that describes the amount of the isotope in grams remaining at time t, where t is measured in years. Okay, so I'm going to write big C of t. What is my initial quantity?
10.
Very good. What is my exponential factor? 2. Okay. I could write 1/2, but that would make my a less than 1, which would change the sign in my numerator. And I'll show you more later. For now, let's say 2, okay? Because it's halving every so often, and that means I have a factor of 2 that is decreasing by. Okay, I have my negative t in the numerator, and then what is my period of decay?
5,730.
Very good. Never mind. 5,730. And this would be my function C of t. Okay? So, question for you guys. How much C14 is left after 5,730 years? 5 grams. Very good. How much left after 10,140? No, that's not how you say it. 11,460 years. Yes, 2.5. Saying numbers is very hard. Okay, so this is how decay works. And as a general rule, try to keep your exponential function greater than 0. I'll explain why right now. Okay? Question for you all. Let's say we had a function, maybe 5 as our initial value. 5 times 2 to the negative t over 17. Is this a decay function or a growth function?
Decay.
Decay, very good. But now let's say we had a function 5 times 1/2 to the negative t over 7, or positive t over 17. Positive t over 17.
Decay.
Is this decay or growth? Decay, very good. Even though the t is positive, right? Even though the t is positive, this is decay because our a is less than 1. Our exponential factor is less than 1. And so this is actually, we could rewrite it as 5 times 2 to the negative t over 17. It's the exact same as before, so it really is decay. Okay. Let's say we had 5 times 1/3 to the negative t over 18. Is this decay or growth? It's growth, very good. It's growth because even though our exponential factor is less than 1, our exponent is negative, which means that this can be rewritten as 5 times 3 to the t over 18, which we can all agree is growth, right? So something to be cautious about, just because the exponent is negative doesn't mean that your function is automatically decay. You have to also check whether the exponential factor is greater than 1 or less than 1 and determine based on that. So these are some general ways to solve these questions. Any questions up to here? Let us do a more tricky one, but also not that hard. Okay. Okay, the number of bacteria in a petri dish, you guys all know what that is, right? Petri dish is increasing according to the law of exponential growth. The initial population is 80 bacteria, and the population after 12 hours is triple the population after 7 hours. How many bacteria will there be after 25 hours? All right, so we can write our function, maybe capital B of t. What is our initial value? 80. What is our exponential factor? 3, because we're tripling, right? Tripoli. You guys know that's a city in Libya? Tripoli. Anyways, what is our... Okay, so we're going to have a positive t because it's growth. But what is our period of growth?
12.
No.
For 7 hours.
No.
1/2.
No.
25.
No.
6 hours. 5.
Yes. And how do we get 5?
12 minus 7.
Okay, thank you. Very good, right? So we see here in the question, the population after 12 hours is triple the population after 7 hours. So we can deduce based on that the population is tripling every 5 hours, okay? Because 12 minus 7 is 5. So sometimes you might see some more tricky ones like this, where you have to kind of deduce the period of growth from the question. And this would be our function, and then we could find our answer. B of t equals, B of 25. B of 25 equals 80 times 3 to the 25 over 5, which is 80 times 3 to the 5. Anybody want to do this in their head? I don't think I can. My multiplication is really bad.
$10,000. 19,440.
What is it?
19,440.
Seems right. Any questions about this? All right. Yes, you can take a picture. All right. Yep. Unfortunately, we're not done. We have to learn 2 new functions. All right. We are going to learn about we don't have to learn it that deeply, but we do have to know it for the test and for the homework. It's something called a Gaussian function. You guys learned this before? You can call it a Gaussian function, a Gaussian distribution. You're going to see this all the time if you take stats or pretty much any field of science, right? This is also known as a bell curve. You guys know who Carl Friedrich Gauss was?
A man.
Yes. Well, he was a very famous mathematician, but he was famous for calculating 1 plus 2 plus this plus all the way to 100 when he was like 5 years old in his math class. Can anybody do this?
Wait, I know a formula for that one though. I remember, wait a minute. What formula is that?
Anyways, the Gaussian function is written as this. Y equals a times e to the negative x minus b squared over c. Daunting, but very important function actually. This is probably the most useful math thing that you'll learn ever in this class. And that's not saying a lot, but...
3 powers. No, 2 powers.
Okay? And I'll show you how to graph this.
He was 5 years old.
Huh?
He like made this.
No, when he was 5, he did this question.
Wait, so what? What am I doing?
Can you do this when you were 5?
Oh yeah, actually, that's right.
Okay.
What happens if someone told him the answer to that and then he went to his class?
I think he was just smart. All right, I'll show you guys how to graph this. Okay? So to graph this, well, we don't have to know exactly how we graph it, but I'll show you how. to graph this, three things are very important. The first is its value at x equals b, okay? Anybody know what this value would be at x equals b? If we plug in b for this equation?
Negative b squared divided by c.
Nope, not quite. It would be a times e to the negative b minus b squared over c, right? But this exponent is just 0, right?
So
So it's just
one.
a.
It's 1.
A.
1, yeah.
A times e to the 0, right?
1a.
Wait, how did the e get rid?
Because the exponent is 0.
Oh,
Minus b squared. Okay, so we know we have a point here at a. And then something else that we can also notice is that when x tends towards infinity, y goes to 0. And when x goes to negative infinity, y also goes to 0. You can verify this on your own time. I'm sure all of you will do that. Okay, and so the graph is going to look like this, a bell curve. Right, so you guys see the, you guys know like IQ distributions, those are bell curves. Pretty much any distribution is all bell curves, if it's random to some extent. So you see this a lot in stats. Okay, but the only thing you need to know for the test is the name, Gaussian, and you need to be able to recognize the name after you see the equation. Or you need to be able to know the name from recognizing the equation. And you also need to know what the graph looks like. You need to be able to draw the shape of this graph. Okay, so where is the horizontal asymptote of this graph?
0.
Nobody has said it. Y equals 0. Okay, horizontal asymptotes, you always need to say y equals. All right, second function to know, the logistic function. Logistic function. That is y equals, I can never remember what they have here. Y equals a over 1 plus b times e to the negative, what is it, rx? Yeah. Okay? You need to be able to know the name from recognizing the equation, and here's how we graph it. The logistic function has two different horizontal asymptotes. As x goes to negative infinity, y goes to 0. And as x goes to infinity, y goes to a. Okay, so we're going to have two horizontal asymptotes. And it's going to look like this. And this function is also super useful because it describes a lot of like wildlife populations, any kind of population, because this horizontal asymptote y equals a is known as a carrying capacity. So you can think about some example, like maybe you're introducing like wolves into Yellowstone National Park or something, and you start at 0 wolves around here, and then you introduce some wolves, and then they grow and grow, but they do end up reaching a certain carrying capacity, right? Because the number of wolves cannot just increase forever. It's always limited by some factor within the environment. And so it'll reach, but not quite approach. It'll approach, but not reach that carrying capacity. And so the growth of the population will typically look something like this. Any questions? Yeah, Liam?
So that graph's similar to like the speed of a car where it keeps on increasing until it reaches max speed and it stays the same.
Yes, but that would not really be described by this function. Yeah, but it's a similar shape, I guess. Okay, so on the test, I've taken a screenshot of the test and I've put it right here. This is all you need to do. You're going to get 5 equations. These 5 equations, this is literally a screenshot from the test, okay? You're going to get these 5 equations, and you need to write the name of the model and draw a simple sketch of the graph, okay? So for this, you would write, what is this? Exponential growth.
Shoot.
And then you would have to draw a simple sketch of the graph. This is exponential decay. Okay, guys, I'm giving you test answers here. Exponential decay. Those are easy. What is this?
Gaussian. Gaussian.
Very good. Gaussian?
Wait, Gaussian or wait,
Gaussian.
No. Gaussian. Okay? And you have to draw it correctly. A bell curve. Okay? If you draw it here, it's wrong. -1. If you draw it here, it's wrong. If it's shifted, it's fine. This is fine. Okay? That's the Gaussian. What is this one? Logistic. In this one, you have to draw the asymptotes at the right place. So it would be something like this. Okay? This is wrong. That's wrong. If it dips below the x-axis, it's wrong. This is wrong. And then finally, we have our logarithmic function. You all know. Questions?
those are like the last questions of the test?
Yeah, my throat is dying. This is the last page of the test.
And the test is 18 questions?
I guess so.
Don't say just that's it, bro. These questions are gonna be held in like 18 of them. Longer.
That's enough.
Yeah, keep it down.
I'd rather separate them.